initial.
X initial.
X initial minus X final. Now when you write this in there, how do you measure X? Because you have to be careful when you talk about the X of a spring. Because it depends on where you put the origin, of course.
So you either use X as the radius?
So if I take on the x-axis here, and I have my spring in there, so when we talk about X, it's going to be, for instance, this location here. Where should I put the 0 for this formula to work?
The area of the equilibrium?
Right, so you need to have the 0 here. This would be the rest position of the spring. If you don't put the rest position at 0, this formula doesn't work. You would have to put in there xi minus x naught square on xf minus x naught square. You have to be careful with that. So in general, we put the 0 at the rest position. So here.
Delta X initial.
Right, square. But you have to be careful actually for the formula because you see it comes from this. So it comes from doing that integral. You would say from xi to x final of k x minus x naught and then times the dx. So this is what you have to integrate. So if I have x naught is equal to 0, I see immediately that I get 1/2 kx squared over 2, which is what is over there. But now, if you have here x minus x naught like this, you have to work with this. So what you can do a change of variable. You can call u is equal to x minus x naught. What is du? So I do a change of variable. I'm just doing a change of variable so that we can see how the integral is going to give us a formula over there. You guys know how to do change of variables and so on in integrals and things like that? So what would be du then?
0?
Du
Minus 1.
dx.
For x naught, dx, yeah, x naught is a constant. So it would be just dx. So you see that this integral can be rewritten as k u du. And now the bounds would be, well, you have x is equal to now u plus x naught. Well, I can just leave it this way. U is equal to x minus x naught, I didn't need that. So when you have here x final minus x initial now, that would be our u final. And u initial would be x initial minus x naught. So now you can integrate this. This is going to be just 1/2 k u squared over 2, and between the bounds. So you get the formula that we get here, but with xf minus x naught on xi minus x naught. I don't get the right sign because here I should have put a minus sign to begin with, because the work done by the force, if it is pulling and dx is positive, is going to be negative. So this is because we have negative work. But what you have here would be if not, so if x naught is not 0, you would say xi minus x naught square minus x final minus x naught square. And it comes naturally from the integral. So this is for the introduction, what there is to review about work and so on. So now let's see how we can put this to good use. So there's nothing new with work. It's still F net is equal to MA. But what is nice, there are some problems where you can use a work energy theorem. So you don't really need to look at the details of what is happening in between. And you can find the final velocity very easily if you know the amount of work done on the system. And because of these formulas, we can easily find the amount of work done if you know where the system is initially and where it's going to be at the end. Not always, but sometimes you can. If you're looking for an amount of time, that doesn't help you. So you cannot solve all of the problems with this, but some problems can be easily solved with the work energy theorem. So now let's turn to chapter 14. So we can start with number, let's do number 14 now, because we know blocks now with pulleys. So 1414 on page 175.
Bài cô thì nhớ một cái làm sai cái thôi.